Today, I'm going to talk about introduction of our project. In recent decades, wind turbine technology has rapidly advanced, largely driven by innovation in aerodynamics, structural dynamics, and micrometeorology. These developments have resulted in a consistent 5% annual improvement in energy yield, enhancing wind power generation efficiency. As research methods refine, turbine designs have become lighter, stronger, and more efficient. The installation of wind monitoring stations allows engineers to gather precise data on wind patterns, aiding the selection of optimal wind farm sites and suitable turbines for local conditions. Design advancements such as larger rotor blades and taller towers further increase efficiency. Additionally, improved machining techniques make components more cost-effective. Wind turbine performance improvements stem from two key areas: better predictive maintenance and enhanced operational procedures. These advances lead to reduced downtime, higher availability, and optimized efficiency. The addition of larger machine turbines for low wind areas and new material contribute to these gains. Government plays a crucial role by offering policies and incentives that support renewable energy investment, driving progress toward greater sustainability and energy independence.
Design process. The design process for the wind turbine begins with through research and planning, focusing on the specific objective of the project. The primary goal is to ensure a smooth design process and to identify the functional requirement of the wind turbine. Research on the design and operational principle of wind turbine, particularly horizontal axis and vertical axis type, is crucial at this stage. Horizontal axis wind turbines are typically used for large-scale power generation, such as in wind farm, while vertical axis turbines are more suited for small-scale applications like urban areas. Understanding this variation helps in selecting the most suitable design approach based on the project requirement. During this phase, the concept for each component, including the base, rotor, blade, mast, shaft, washer, and housing, is outlined and refined. Next, using SolidWorks 3D modeling software, we begin to develop individual components for the wind turbine. The modeling process starts with creating detailed parts such as the base, rotor, blades, lower and upper mast, shaft, washer, and housing. Each component is carefully modeled to ensure that it fits together in the final assembly. SolidWorks assembly feature is then used to bring this part together, allowing for a complete representation of the wind turbine system. This 3D model allows us to simulate the interaction between various components, ensuring that the turbine functions properly when assembled. The software also offers the ability to visualize the assembly, helping to identify any potential issue early in the design process. Lastly, steel is chosen as the material for the majority of the turbine component, particularly the blade, due to its strength, durability, and cost effectiveness. Steel is known for its ability to withstand harsh weather conditions and environmental stress, making it an ideal choice for a wind turbine component exposed to outdoor elements. Additionally, it offers a good balance of performance and longevity, ensuring that the wind turbine will function efficiently over time. By using SolidWorks for the design and analysis process, we can optimize the turbine component for strength, efficiency, and overall performance, ensuring that the wind turbine will meet its intended purpose. Design process. Initial sketch, which is housing. The housing was purposely to protect internal components while providing mounting points for the upper and lower mast. The first interaction focused on fitting the components securely inside the housing. Next, initial sketch washer. A washer may be used where the rotor connects to the shaft, ensuring that the rotational force is transmitted efficiently while protecting the connection. Next, initial sketch shaft. The shaft was designed to transfer torque and rotational motion between the rotor and the rest of the assembly, In this first interaction, it was modeled as a simple cylindrical shaft with basic length and diameter parameter. Initial sketch blade. The blade was designed to be aerodynamic with an initial focus on form and fit. Later repetition work refined its geometry for better performance under load. Furthermore, initial sketch, which is base, the base was designed to provide stable support for the rotor and the upper mass. The focus was on ensuring a solid foundation while keeping the geometry simple for easy manufacturing. Next, initial sketch rotor. The rotor was designed to carry the load of the blade and undergo rotational motion. In this case, the rotor geometry was basic, focusing on functionality rather than material optimization or load distribution. Lastly, initial sketch lower mass. The lower mass was designed to provide the necessary vertical support for the system. Initial design choice focus on ensuring adequate height and connection strength with the base. Next, upper mass. The upper mass served as a support for the rotor and blade assembly. In the first interaction, the design was straightforward, ensuring alignment with the lower mass.
FEA analysis. FEM stands for Finite Element Method, meaning a technique by which one determines approximate solutions of boundary value problems for partial differential equations. For an easy translation, FEM means that a very complex problem is discretized as little segments or elements interlinked and when with solution relationships against one another. The FEA will enable the engineers to predict how each individual component of rotor, blades, shaft, housing, upper and lower mass will respond to the applied forces. The insight into highly stressed and strained regions and possible failures help to arrive at an optimized design with better performance and reliability. FEA analysis, which is base. Based on the first FEA results, the base has been strengthened in some areas to ensure better load distribution. Material thickness has been adjusted in an effort to reduce the overall weight but keeping the strength intact. The base was subjected to static loading conditions of the wake of the turbine plus additional forces due to the wind gusts. Low stresses were found around the base attachments, points colored blue in the FEA results below. This value is larger than the yield strength of the base material, 4.600E plus 0.1, indicating possible failure to these highly stressed regions. Regions of the base that saw low stress were candidates for material reduction to save weight and reduce costs without compromising the necessary strength and safety. FEA analysis. Blade. For this part, the blade is confirmed to operate under low stress, blue colored, and medium stress, the green colored, within the material safe limits. Material thickness was reviewed with the potential reductions in areas of low stress to decrease the overall weight of the blade and improve the turbine efficiency. FEA analysis. Lower mass. The lower mass was redesigned to accommodate stronger attachment to the base and the upper mass. Extra stiffening was required to ensure its stability under the dynamic forces applied. The lower mass, which sustains the weight of the upper mass and the dynamic forces due to wind, presents higher stress concentrations, especially at the place where it's anchored to the base of the turbine. The FEA gave maximum stresses in these regions, which are near the yield strength of the material, 4.600E plus 0 plus 8, showing possible failure in the case the applied loads are higher than expected. This confirms that the lower mass is subjected to the low stresses and stays within the material's operational limits for safety. Besides, regions of low stresses were found where, especially in the non-critical areas, materials could be reduced to lower the weight and material cost while still enabling the mass to serve its purpose of strength and durability. FEA analysis, upper mass. For this part, to reduce the stress from medium stress to low stress, we need to change the material to a stronger material and replace the current material with the one that have higher yield strength. Other than that, redistribute load by adjusting the angle or direction of applied loads. FEA analysis, housing. For this part, housing was under low stress and considered safe as we can see that the part was completely blue colored and there is no any modification. Since the housing operates safely with low stress, the possibility of reducing the thickness of the washer was considered for material and cost saving. FEA analysis, washer. Based on the FEA result, the washer is under low stress and performs well within its material safe limits. The washer's design does not require any modifications as the stress levels are far below the material yield strength. Since the washer operates safely with the low stress, the possibility of reducing the thickness of the washer was considered for material and cost savings. The reduction in thickness will not affect the performance as it remains well within safe stress limits.
Let's move on to our conclusion. So this project demonstrated the practical application of finite element analysis, which is FEA, in analyzing wind turbine performance, enabling the prediction of material and structural behavior under extreme conditions for optimal design and durability. By identifying potential failure points and providing valuable data, FEA guided decision-making throughout the design, manufacturing, and maintenance stage. Despite initial challenge such as limited experience with SolidWorks and FEA, our team successfully created 3D models, analyzed stress, strain, and deformation, and optimized the data, the design to ensure structural integrity and cost efficiency. The project enhanced understanding of force on wind turbine components, contributing to safer and more efficient renewable energy solution.